Alright, today we got solving linear system of equations by graphing. So you have a system of two linear equations and two variables is also called a linear system. Consists of two equations. A solution of a system of linear equations and two variables is an order pair that satisfies each equation. Solutions correspond to points where the graphs of the equations in a system intersect, and that's kind of the big key word that we're going to be talking about today. We're going to be looking for the intersection of two graphs. Okay, so here's a couple of examples of what that could look like. So one solution means it crosses only once. So this would be like an example here, and then you would just write out your solution. You would say it's, I guess, 1, 3 based off of where my two lines intersected there. All right, and then we also have some new vocab here. So we call this system of equations right here, we call this an independent system. Okay. All right, and then you got the two cases that you don't see as often, but infinitely many solutions means they need to intersect. Here, let me draw that different so that doesn't look like the same exact. Yeah, they need to be the same exact line. They need to cross an infinite amount of times, and the only way that happens is if they wind up being the same exact line right there. So I kind of like to overlap the two lines so you can kind of see the difference right there. So infinitely many solutions, by the way, we sometimes abbreviate this with IMS, so you can do that if you would like as well. And we call this a dependent system. Okay, and then the final one is no solution, so they can't cross at all. So when that happens, typically that means your lines are parallel. So if you have parallel lines, you'll have no solution, and we call this an inconsistent system. And that is it. One thing too, going back here to the dependent system, you might want to even write this down here. If the lines are overlapping, obviously they're the same line. Now sometimes they'll look a little bit different. We'll get examples here a little bit later that the two equations look different initially, but after you go and solve, you're going to go and find out that they wind up being the same exact equation. So let's go ahead and do a few of these here. So we're going to graph the following equations, find the point where they cross their intersection, and then we're going to check our solutions. So since I don't have a whole lot of room here to work, I'm just going to rewrite this here to the side. And remember, to graph any type of line, we need it in the format of y equals mx plus b, which essentially means we need to get our y by itself. So we're going to do that in one step here, or actually a couple steps, by subtracting 3x. So that'll be negative y is equal to negative 3x. Be careful with this negative here. You got to drop that down there to the bottom. And then to get rid of a negative in front of y, we can divide both sides by negative 1. Now we'll flip our sides around. So we'll get y equals 3x. And then we'll go graph that here in a second. All right, this other one here I'll do here in red, and I'll just go ahead and start working it right here. I'm going to subtract x from both sides. So that'll be negative y is equal to negative x minus 2. And then since the x and the negative 2, they're not like terms, so you can't really combine them. You just write them next to each other like that. And then we're going to divide everything by negative 1, which will flip all of the signs around. So that'll be y equals positive x, because a negative over a negative, and then a positive 2. And then we're going to go and figure out where those cross. So now remember, when you're graphing y equals mx plus b, m is the slope, which is also rise over run. So how high up and how far down. Now if it doesn't have a number out in front, like this first one here, it's implied to be a slope of 1, which you can also write as a fraction as 1 over 1. So our slope is going to go up 1 and then right 1. Okay, and then the b is the y-intercept value. So if like b on our red equation here is 2, we're going to start at 2 on the y-axis. So we'll start there, and then we'll go up 1 over 1. Bunch of points. Now, since I don't know exactly where these are going to cross, I'm going to put a bunch of bullets here. Because you want to use those to figure out where something crosses. If you kind of use your line and you don't draw your line straight enough, you might get the wrong intersection. So make plenty of bullet points. If you need to add more later, you definitely can. Now this other one right here is just y equals 3x. It doesn't have a plus anything, so it's kind of like a plus 0, which means it goes through 0 on the y-axis, or you could even call that your origin. And then the slope of 3, that's kind of like 3 over 1. So that's going to go up 3 units and right 1. Which is the point right there. Up 3 over 1, up 3 over 1. You can go down and left if you run out of room. It's always a good habit to get a couple of points. And then draw your line. And we're looking for that point where they cross, which is right there. Sometimes I'll circle that there. So our solution looks like it's 1, 3 in this case. Okay. Now, we're not going to do this on every single one just due to time, but you can go back and check your solutions. So we are going to go and do that with this one here, and we check our solutions algebraically. So we're going to go and take that 1, 3, and then we're going to plug it back into our original equations right here. So I guess let's do the first one we worked with. I guess this one right here, 3x minus y equals 0. And then we're going to plug in 1, 3, and 1 is our x, and then 3 is our y. So we're going to go 3 times 1, and then minus our y value 3, and then see if that equals to 0, which, obviously that's 3 minus 3, which does work right there. So that first solution works, but we have to make sure it works for both equations when we're checking. So we're going to go back here to x minus y equals -2, and we're going to check that solution. Some people will just skip this first step and just plug the numbers in right away. You can do that as well. There's really not a whole lot of work to show there for that. 1 minus 3 is definitely -2, so that one works out there. And that is a solution. So we're going to do this a couple more times here. To do that, let's see what we got going on here. We got 3x plus y is equal to -2. Should write it like this here first. X plus y is equal to -2 since I don't have any room. And then we'll subtract 3x from both sides. So that's y is equal to -3x and then -2. So that is our first equation. We'll graph that here in a second. And let's see what's going on here with this other graph. This other one here we'll do here in blue. So -6x from both sides. So that's 2 y's left over. -6x and then +10. And remember, -6x and 10, those are not like terms, so we just write them side by side. And then to get rid of this 2 out in front, we're going to go and divide everything by 2. So that would be y is equal to -3x and then +5. Okay. So now we will go and graph those. Now, if you're looking closely at the equations, you might be able to tell something about them because they do have the same slopes here. And that means something's going to happen when we go and graph them. So some of you guys might already kind of know. It's fine if you do. We'll get a few points going here. There we go. See if I can kind of get a straight line going through them. So there's your line right there. It keeps going forever, so put your arrowheads on it. The other one starts at -2 and then down 3 over 1. So notice here that your lines look like they're never going to intersect, and that actually has to do with the slopes here. Since the slopes are the same exact thing right there, we can instantly know that they're going to be parallel. And that's only if they have different y-intercepts. Now, if those y-intercepts wound up being the same, those would be overlapping lines, which I do think we see an example here in a minute. But they have different y-intercepts. Obviously, they're parallel, so they're never going to cross there. So when that happens here, you don't leave it blank. You need to write out that there is no solution for this that's what you would put in an answer box. So, and I kind of forgot to emphasize this. Answer box for the first one there, you're going to go back and put 1, 3 for your solution. So, all right, 2 more of these here. So let's see what's going on with these. So we'll go 5x minus 2y is equal to negative 10. We will subtract 5x from both sides. Don't forget to drop down that negative with the 2. Okay, and then divide by negative 2. And don't forget, whenever you have a negative divided by a negative right here, that should become a positive right there. So we should cancel these out. Yes, 5 over 2 doesn't reduce, but we can write it as 5 over 2x. And then 10 over 2, I guess, is going to be plus 5 right there. All right, and some people might see, oh, okay, we got fractions, kind of freak out when they see fractions, but whenever slopes are fractions, it's really not hard. It means just up 5 and right 2. So that shouldn't be too bad. Let's see what's going on here with this other one. We're going to subtract 2x from both sides there, so that's negative 4y. It's negative 2x. And that is plus 12 right here. Okay, and then to get rid of the negative 4, we're going to divide everything by negative 4. Okay, so that's y. 2 over 4 does reduce a little bit. Reduces down to 1/2, but the 2 negatives will cancel out. So we'll say 1/2 x. 12 over negative 4, that should come out to negative 3. And there you go. There's your 2 systems right there. Now, if you look closely, different slopes, so we know that you're eventually going to intersect somewhere, hopefully on our graph. So we're going to go ahead and graph that. First one here in blue, the y-intercept, negative 3. The slope is 1/2 from there. Go on our y-axis. Start at negative 3. And then go, I guess, up, what was it, 1/2. So that'll be up 1, right 2. And if you run out of room, you can also go down and left. And then since we don't really know where they're going to intersect, I'm going to do quite a few points. Okay, now in red, we have the 5/2 x plus 5. That means it starts at 5 on our y-axis. And it was up 5 and right 2. So that means we can also go down and left. So down 5, left 2. Down 5, left 2. Down 5, left 2. There you go. So it looks like it intersects at that ordered pair right there. And what is that? That is, looks like negative 4, comma, negative 5, I guess. That'll be good there. All right. Last one right here. Let's see what's going on. This first one right here, negative 4x plus y equals 5. So we can actually solve this for y in one step. We're going to add 4x to both sides. There we go. And that would be our first equation. Now this other one here, notice how everything's on the left-hand side and they just have 0 on the right-hand side. So we need to move everything that's not y to the other side. Or I guess another thing you could do is just move the 2y to the other side, but then everything's reversed. That kind of throws people off a little bit. But whatever you want to do. Whoops. So we're going to add 8x to both sides of our equation. Make sure your reference point is that equal sign there. You need to add to both sides of that right there. And we can also just do this in the same step. We need to add 10 because we need to cancel those out. So we'll also put plus 10. So you're going to have 8x plus 10 on the right-hand side. And then on the left-hand side, all we're left with is 2y. And then now it's kind of looking a little bit more like something we've dealt with. And if you have 2 times y, divide by 2 to cancel those out. So that gets us 4x plus 5. Now notice here, these are the same exact equations. So before we graph, we can hopefully are going to recognize that this will have infinitely many solutions right there. If you want to spell it all the way out, you can. If you just want to write IMS, you'd probably be fine as well. Now if you got slope of 4, it's kind of like 4 over 1. So that means up 4, right 1, or down 4, left 1. through right there, and then if you want to add in some points there, kind of just sketch to show that the lines overlap, you can. Because I know in the notes it might, if you only see one, you're kind of going back and looking through your notes. I'm not sure if you'll catch that there, but yeah, you want to show that the lines are overlapping there, and then infinitely many solutions written. Okay. So this next one here, we're actually going to do a word problem here, tying it in with solving systems of equations by graphing, but actually you're going to use our graphing calculator a lot on this one. But before we begin, we need to figure out what we're going to type into our graphing calculators. So let's see what we got here. The diagram shows the birth lengths and growth rates, I can't talk, of two species of sharks. You have the Greenland shark and the dogfish shark. So they got a rate going on right here and then a starting amount. So we can actually write our equations here in y equals mx plus b form. So if you think about it here, if you think about like your growth rate here, you can say like you start at 37, and then each year they're adding on 0.75. And then since it's each year, typically in Algebra 1, we told you guys to put an x with that right there. So it's 0.75 times each year right there. And just to get it in the format of y equals mx plus b, we'll swap the order around. So we'll do 0.75x plus 37 right there. Okay, and then let's get our other one going here. I guess I'll color code it. So the spiny dogfish shark, or the spiny dogfish shark, I guess. So this one here, you're starting at 22, but then you got that growth rate of 1.5 per year. So we're going to go 1.5x and then plus 22. Now, if you were actually trying to go and find the actual intersection of the graph for these, it would be kind of tricky because we wouldn't have a graph with enough grid points to where we could actually see where they cross. So we're going to use our graphing calculator for that. Now, before we do that, we want to kind of think about what the x-axis and what the y-axis mean in this situation here. So if we have 0.75 times our x right there, x is it's 0.75 centimeters per year, so x is actually going to be your years, which means the y-axis is going to be your centimeters right there. And you can also use the fact that, hey, the starting amount is centimeters. It's like kind of like your y-intercept, right? So you can say the starting centimeters, I guess. I guess we'll call it the length right there. So you got the length versus the years, and then we're going to try and find an intersection. So for a second here, I'm going to kind of pull this to the side, hide this for just a second, and see if we can get this going in our graphing calculators. So your normal graphing calculator screen kind of looks like this here. So we're going to go out to y equals, and if there's anything typed in right now, you can just go and clear it out. And we're going to type in our new equations here. So we have 0.75x, and then what was it, plus 37. I'm just getting that from the two previous equations we got. The other one was 1.5x, and then plus 22. So those are your two equations, and then what's kind of weird about this is when we hit graph right away, this little yellow circle is saying it's loading, it's graphing it right now. We can kind of see one of our graphs, but we can't see the other line. That's because we're zoomed in too much. If you think about it, our y-intercepts are 37 and 22, so I actually can't see it. So there's a couple different things you can do. You can hit the zoom button, and then you can zoom out, but sometimes that might not zoom us out enough. So what I like to do sometimes is go to this window button here. It's in the top. So hit window and then change your maximum and minimums on your x. So like x min and x max, that's just like how far to the left you can see and how far to the right. It's kind of like your interval notation. So right now, currently our graph is set to where we can see 10 units left and 10 units right. And then same thing with the y's. The y right there is -10, so 10 units down, 10 units up. So I think, especially since our y values, like our y-intercepts, are starting at like 37 and 22. So I'm going to change that y max, maybe to like something like 100 here. So I'll add an extra 0 there. Probably for the x max, we'll do the same thing. And then I'll hit graph, and hopefully we can see the full setup. Yeah, there we go. So now we can actually see this intersection. And here's the issue. I'm not even sure if they put all of the ticks here, but it's kind of hard to count all the different ticks, and I'm not even sure if they're all technically showing up, because there should be technically like 100 or 110 of them right now, which is a lot. So to get our graphing calculators to actually tell us where the intersection is, we can hit second, and then this trace button here, it's that blue option, calc, so second trace, and then we're going to scroll down to intersect, so you can scroll down, or you can just hit 5, doesn't really matter, and then enter, and then they're just going to ask you, okay, is this the first line, which yes it is, is this the second line, yes it is, and then guess, we're not going to guess, so we're just going to hit enter one more time. And apparently the intersection is 20, 52. So let me see if I can get my air server going here again. Not sure if it disappeared. It looked like it did. So bear with me 1 second here. Apologize. Okay, cool. So that intersection was 20, 52. So that means in 20 years, their lengths will be the same at 52 centimeters, and that's what we're trying to find. The growth rate stays the same. At what age would a spiny dogfish and a Greenland shark be the same length? So 20 years. I guess I kind of forgot to read the actual question, but yeah, we're trying to figure out when they're going to be the same. So 20 years. Okay. So that's a bunch of good little things there you can do with the graphing calculator. Sometimes it's a little bit quicker just to go and actually graph it by hand. But on these word problems, sometimes it's pretty helpful. Follow-up question they have, if the growth rate continues, how long would each shark be when it's 25 years old? So this is actually something we're going to do algebraically. So we're going to use our two equations, or actually let's use that second one there. We're going to use these two equations right here to go and figure out what's going on in 25 years. And then since we said the x-axis was like your years right there, that means we're going to plug in, for the x, you're going to plug in 25. So I'm going to bring that down here. We'll color code it since it's kind of like a two-part question. So it's y equals, what do we have? Oh yeah, 37. So it's 0.75x plus 37. And then we're going to go ahead and plug in 25. And plus 37. And I could probably figure out the math on that, but I'm going to go ahead and pull up my calculator here on my phone. So 0.75 times 25 is 18.75. And then we'll add on the 37. And that gets us 55.75. And that would be, I guess, the length of the green one. Yeah, the green one, the Greenland shark. Okay, and then the spiny dogfish. What was our equation? So y equals 1.5x and then plus 22, I believe. Yep. Okay. So this one here, we'll plug in 25 again. So 1.5 times 25 gets us 37.5. And we're going to add on our 22. That gets us 59.5. And then usually, especially with these word problems, it's good to put units. So that'd be 59.5 centimeters, and then this one would be 55.75 centimeters. And those would be your two solutions there. Now, actually a pretty good follow-up question here. Explain why growth rates for these sharks may not continue. Definitely. Like, obviously, we got a shark, it's going to grow to a certain length, but then it's going to hit that top end cap, I guess, and he won't be able to grow past that there. So, maybe this model is not even good for 20 years. Maybe it's only good for 10 years. Maybe it has that growth rate, at a shorter time period. So, I would just say sharks don't grow forever, I guess. All right, awesome. Okay, couple more things here. We're going to classify systems without graphing. So we're going to go back to independent, dependent, and inconsistent systems. And, just a recap on that. Here's what they look like. Independent, remember that crosses once. Dependent winds up being the same exact line. And then inconsistent is when they don't cross at all. Okay, so it's one of the few things you need to study for in this unit here. So let's go through this here. Without graphing, how could we do that? Here are your steps. So there's a couple different ways you can do this, but the way I'm going to teach you guys today is you're going to solve your equations for y. And then after you solve for y, you're going to compare the slopes. And actually not even the slopes and the y-intercepts. So think about this here. If you have the same slope and you have different y-intercepts, that means you have to be like two parallel lines, and parallel lines we said never cross there, so that would be your inconsistent. Okay. Now, if you have same slope and same y-intercept, that means that those are the exact same equations, which means we call that a dependent system. Okay, and then if they don't have the same slopes at all, which is actually the easiest one to identify, let's just say different slope. And it doesn't even matter if they have the same y-intercept or not, but if they have different slopes, that means it's an independent system. So that would be good to write down, and then we're going to go and actually apply it here on, I think, 4 of these. So, all right, let's look here at the first one here. Notice it's kind of in a weird order. 4y minus 2x equals 6. I guess the x and y are a little bit different order, but that's okay. We'll add 2x, add the thing that's not y to the other side. That's 4y is equal to 2x plus 6. Not like terms, right? And then divide by 4 to cancel out your 4's. And the first one reduces a little bit. That's 1/2 x. And the second one actually reduces 3/2. And initially, it might kind of look a little weird. And we might think, oh, that's going to make the problem hard. But really, we're paying attention to the slope right now. That's your slope, and then we're going to go and see if the other slope is like that. So I'll do that here in a different color. Now this one right here, it's actually where you have y, you almost have it by itself here. All you got to do is divide by 8. Okay, so that'll get us y. 4/8 reduces to 1/2. They're both divisible by 4, right? And then 12/8, those are also both divisible by 4. You could go 3/2. Okay, so once again, compare the slopes there. So you got 1/2, and then you got 1/2 right there, so the same slope. Now, the y-intercepts here, really close, but slightly different. One's positive, one's negative. So that means since they're the same slope and different y-intercepts, we're going to say that is an inconsistent system. There you go. It kind of gets a little jumbled up here, so I'm going to draw a little line. Okay. Let's see if we can do a different color here. All right, next one here. Let's see. This one we can actually do pretty quick in one step. We need to cancel out our 3x. We can do that by adding 3x to both sides. That's why it's 3x plus 4. Okay, second equation, this one's going to be a few steps here. I'm actually going to bring it over here to the right more. This is x minus 1/3. Actually, let's differentiate our colors. X minus 1/3, y equals 1. Okay, so this one's got a couple weird steps we haven't seen. This is good practice for solving for y. So we'll subtract x from both sides. It's negative 1/3 y, and then I guess we can put negative x and then plus 1. Okay, and then to get rid of this negative 1/3, we can multiply by what we call the reciprocal, so 3 over 1. But then to also take care of this negative at the same time, we can multiply by a negative. So negative 3 over 1 or negative 3. But then we have to do that same thing on the right-hand side, which is actually going to induce some distributive property over there. So let's start on the left side. Negative 3 over 1 times negative 1 over 3. Everything's going to cancel each other out, the negatives and everything. So that'll give us y. I guess we'll do it here in purple. So y equals, okay, over here on the right-hand side, negative 3 times x. That's going to get us positive 3x, negative times a negative. And then negative 3 times 1 is going to get us negative 3. And then that would be your equation. So notice here, once again, these slopes are the same, but then your y-intercepts are different. So that means we have another inconsistent. They're going to be parallel, right? So if they're parallel, it's going to be an inconsistent system. There we go. And then just rinse and repeat. All right, next one here. I think we got 2 more, so kind of go through a little quicker. That's 2x plus 3y is equal to 1. We'll subtract 2x from both sides. You can write out all the full steps if you want. You don't need to. We'll divide everything by 3, and that gets us negative 2/3 x, and then plus 1/3, I guess. And we're going to see what's going on here with this other one. And actually, we can do this in one step here. We can subtract 4x from both sides. So y is equal to negative 4x minus 3. Okay, so obviously, if you look here at your slopes, different slopes. So if they're different slopes, that means they're going to only intersect once. We call that an independent system. All right, last one here. Nice thing is the first equation's already solved for us. So that is very nice. We don't have to do anything there, so the slope is 2. And then we're going to do this other one over here, 6x minus 3y equals 9. We start out by subtracting 6x from both sides. Don't want that there anymore. And then divide by negative 3. And then just be careful with your negatives. Negative divided by negative should be a positive. So it should be 2x there. And then 3 divided by negative 3 should be minus 3. Or I'm sorry, 9 divided by negative 3 should be negative 3. Alright, so that's your equation. Now look here, these are the same exact equations. Same slope, same y-intercept. So these are your overlapping lines right here, and we write those are a dependent system. All right, and I believe the last, I believe the last one here that we are doing here is explain how you would write a system of equations that result with no solution. So really, just need something that means no solution means same slope, but then different y-intercept. So like if you wanted to write an example, you could do something like, I don't know, like 10x right there for your slopes. But then just make sure one's got one y-intercept and one's got another. There you There you go. So 10x minus 5, 10x plus 15, same slope, different y-intercepts. Those would be parallel. So that's a big thing I guess you're looking for there. All right, and that is it here for today.